So yeah, thanks everyone for joining. Just to briefly introduce, we've got Adrian Harkness here at Lehigh University. He's a PhD student, but also been working at Pacific Northwest National Laboratory. And I just learned that they have a location in New York City where he spent this time working with them. But yeah, excited for you to share a little bit about this benchmarking work in the fault-tolerant space. Yeah, take it away.
Thank you so much. So yeah, I started working with PNNL at the start of the summer, and this is essentially my first project that I've kind of pushed out with them. Um, okay, can everyone see my screen?
Yes, it's coming through good.
Great. Um, so yeah, today I'll be talking about our recent reprint and software package, FTCircuitBench. Um, and it's a benchmark suite that we've been developing specifically designed for the fault-tolerant quantum computation era, which is meant to help kind of evaluate compilers and architectures. Right. So uh, I think the perspective in the field has really shifted in recent years uh, to be that many of our kind of killer applications and most exciting algorithms are expected to necessitate fault-tolerant quantum computers. And this is almost always enabled through quantum error correction. Uh, there are many architectural proposals for making this happen, and each of them have kind of unique trade-offs in terms of space-time costs and other resource costs, and many of them have their own parameterizations for how exactly to implement them. And in many ways, this is a good thing. It gives us a large kind of design space to explore, but also it can become kind of increasingly overwhelming when there's just more and more architectures and quantum error correction codes and computational models proposed each day. And we need some way of kind of starting to narrow down on uh, kind of good pipelines and combinations of parameters. Um, and this is especially difficult because most researchers, at least speaking for myself, are not really naturally full stack in the sense that maybe they're specialized in algorithms or they're specialized in error correction codes or maybe even like RZ gate decomposition, something as specific as that. But it's hard to really know how all of these parameters um, play with one another. And that can make this landscape of trade-offs quite hard to navigate. And we've especially seen that optimizing these parameters at each kind of specific stack in the quantum computation stack does not necessarily lead to kind of a global optimization of parameters when you put it all together. And one example that I like that I certainly did not make up myself, but I read in a recent paper, I believe, called The Grand Challenge of Quantum Applications from the Google team, is that oftentimes a rule of thumb, at least coming from the NISQ era, is to focus on reducing circuit depth and the number of qubits. And this sounds reasonable, but if you just directly port it over to kind of the logical computation side of things, um, this rule of thumb can often be insufficient and sometimes even actively harmful. For example, there are many places where uh, aiming for fewer logical qubits comes at the cost of increased circuit depth. And if that is true, then the code distance may need to increase, which in turn can result in larger physical qubit requirements. So kind of your original goal of reducing the number of qubits totally backfired on you, and now you have more qubits than you started with. This is like a very simple example, but just illustrates how some of these parameters really are not super intuitive. Um, and yeah, so this motivates our work here, uh, and basically motivates benchmarking fault-tolerant computational models, especially with algorithms that we expect to have high impact in the fault-tolerant era. Um, Now we have many benchmark suites designed for the NISQ era. For example, Chasm Bench, which I personally was not involved with, but came from our group at PNNL. But we lacked the same kind of standardization for fault-tolerant quantum computing. And especially in the early fault-tolerant era, we're still very much working with limited computational resources. So it's in a way more important than ever to optimize them through kind of co-designing across the computational stack. Um, so I think this is pretty obvious to a lot of people, but there's a large gap in benchmarking from NISQ era to the era of fault tolerance. Basically, the metrics that we use aren't the same. The algorithms that we are interested in aren't the same. Um, and yeah, NISQ constraints and optimizations do not even closely resemble fault tolerant constraints and optimizations. So, for example, metrics that we tend to want to minimize in the NISQ era involve like 2-qubit depth. Usually, we think of CNOT gates as being very expensive. Um, and maybe we're very worried about physical connectivity on our chip. Um, and oftentimes we're compiling our NISQ era algorithms to kind of parameterized continuous angle gates. And that's fine for NISQ, but obviously doesn't really work like that for fault tolerant quantum computation. And also, we're very often only restricting ourselves to focusing on kind of bounded depth circuits, which makes sense for NISQ again, but uh, we know we have algorithms and applications with kind of uh, a stronger case for quantum advantage that we are certainly interested in benchmarking for fault-tolerant architectures. So here I just have like a Google image of a variational algorithm, which I'm sure we're all familiar with. But this is the kind of thing that kind of uh, very much belongs in a NISQ era benchmark suite and not at all in a fault tolerant benchmark suite. Um, so in the fault tolerant era, we have connectivity between logical qubits, which is not necessarily straightforwardly defined by connectivity of our physical qubits on the chip. Um, we have new cost metrics. So oftentimes Clifford gates are considered cheap. Magic states are now the expensive thing to try to minimize. Um, we have new computational paradigms. So I'll be speaking a bit about Pauli-based computation in the rest of this talk, but this is another proposal that's a bit different than just our straightforward gate-based computational models that translates well to the fault-tolerant era. And as I mentioned, we can really focus now on deep circuits that we've always been kind of worried about even looking at in the NISQ era. Um, so coming from sort of an algorithms background myself, I think to boil this all down to one question, like what is the best way to run my algorithm? I have all these algorithms that I'm excited about. I want to see how they actually uh, look in practice. I want to get away from big O notation and actually see the constant factors. But how do I run it? As soon as you start answering that question, there's so many parameters. So I'll mostly be talking about two leading fault-tolerant quantum computation architectural proposals for the rest of this talk. Um, of course, it'd be nice to benchmark across many more, but we thought that this would be a good place to start. Um, so we know that kind of the gate-based model of quantum computation is universal and well studied, and that's where usually surface codes, which are well suited for the Clifford+T gate set, um, fall. However, there are alternative models that support universal fault-tolerant quantum computation as well, such as Pauli-based computation. And this has kind of risen in popularity recently as a leading proposal, especially because IBM plans to be implementing Pauli-based computation, um, specifically with like the gross code, or which falls in this family of bivariate bicycle codes that they've discovered. Um, and these different architectures and error correction codes uh, have different trade-offs, and it's not at all obvious, kind of given an algorithm, which path is best for running it on. So, for example, with surface codes, we know that uh, they're desirable from a hardware engineer perspective. You only need this 2D nearest neighbor connectivity. Um, However, as a result of that, their encoding rate scales fairly poorly as 1 over distance squared. So that just basically disappears asymptotically. Um, on the other hand, we know that for bivariate bicycle code, such as the gross code, um, it's a QLDPC code, so we have a, a high constant rate. Um, and the trade-off for that comes at uh, increased hardware requirements. Basically, we need non-local degree 6 connectivity for each qubit. Right. So now that we've kind of motivated the need for standardized benchmarking in the fault-tolerant era, as well as kind of narrowed our scope a little bit to these two leading uh, architectures, I can give an overview about what FTCircuitBench is as a software package and as a paper. And I think the best way to think about it is consisting of three distinct components. So basically, we have a benchmark suite of curated, impactful algorithms for the fault-tolerant era, with pre-compiled examples to either of these models of computation, Clifford+T and Pauli-based computation. Um, we also include the tools for doing this compilation pipeline, um, allowing users to compile and decompose their own algorithms if they want to multiple models of fault-tolerant quantum computation, uh, with our own pre-built optimization passes, um, as well as they can kind of build their own optimization passes on top of that and explore what their compilers look like on our benchmark suite. And then along the way of this compilation pipeline, we basically perform numerical analysis, collect statistics on both computational models. And this allows users to evaluate algorithmic and optimization impact across the compilation stack, rather than just one piece at a time. So this includes several kind of visualizations as well. Um, Now, one kind of philosophical approach we have for Chasm or for FTCircuitBench is that we're really not focused on optimizing along the way. So I mentioned we have uh, some included optimization passes, but this is just for PBC circuits at the very end, and it's really not meant to be ultra competitive. It's more just to kind of compare other people's optimizers against. Instead, we're really trying to produce baseline circuits with like level 0 optimization all along the way. And the reason for this is we want these to be kind of things that other compilation researchers uh, compare their strategies against, and then they can say that against baseline we have improved by this much and things like that. Um, And yeah, this is open source on GitHub. Um, I urge people to go check it out, and I'm sure there are probably issues with it, so submit requests and things like that.
Adrian, there is one question in the chat here asking what compilers are included.
So we compile. I'll talk more about each of these kind of core pillars in a second, but like from a high level, we can compile to Clifford+T as well as to Pauli-based computation for arbitrary Cosm circuits. Does that answer your question? Okay.
Where you're welcome, yeah, to come off mute if not.
This is actually maybe a good time for some questions.
So yeah, there's
This
another hand raised too, if you have
okay.
it, Adrian.
Yeah.
Hi. I was wondering what's the end result of the compiler you include in FTCircuitBench? What are you benchmarking? What's the end representation? Is it physical circuit, logical circuit,
It's a
logical
logical circuit.
instruction?
So
Okay.
I could say we abstract away like the kind of actual hardware But we compile to logical circuits in Clifford+T and Pauli-based computation. And you can think of each of these computational models as being particularly suited for uh, maybe the surface code and the gross code, but they can certainly run on other codes as well. So we've abstracted that part away.
I've got a small question. I hope you can hear me.
Yeah.
I've had the luxury of working with some larger circuits with Crack, the simulator, and we found that when we want to run bigger and bigger circuits with ever increasing depth, that this transpiler sometimes just takes a lot of time to look and optimize the circuit. And that is also something that the Pandora project also mentions with regards to larger and deeper circuits. And I wonder, I mean, that's the first question that comes here, because yeah, have you seen that as well? Because that should be part of the benchmark, I believe.
Basically time to compile. Yeah, we have certainly run into very slow compilation times based on, I'll describe in a second, but some of the algorithms that we're including in this benchmark suite are really meant to push the limits of uh, your guys' best compilers, including ours. And for that reason, we actually do include C++ acceleration for some of these key stages, which we've found to be, even though it's running the same underlying algorithm during the compilation stage, it's quite necessary to move to kind of high performance computing tools above a certain circuit size. Any other questions? Okay, great. So I'll be talking about each of these three core pillars in a little bit more in depth for basically the rest of this talk. And please just interrupt me at any point if you have questions. So in terms of the algorithms that we include, it's funny because this is in a way the easiest part of putting together a benchmarking project, just gathering algorithms from, you know, friends and coworkers. Uh, but I also expect this to maybe be the most widely used part of our benchmark suite, at least looking back on uh, projects like Chasm Bench. Uh, it seems like speaking to people who have used that quite a bit, they're very appreciative of just having this repository of standardized circuits to refer to. And that's basically because even if two research papers say that they're uh, running their compilers on the same, say, HHL algorithm, it's almost certain that they don't have the exact same algorithm implementation. They're probably taking quite a bit of time to look through the literature, come up with heuristics for implementing oracles and things like that. So it's really hard to actually compare the results with one another if they're not coming from the same starting point. So the circuits that we include fall into three categories of use. One is basic arithmetic. So this includes quantum adders, ranging from 4 qubits to 64 qubits, and the quantum Fourier transform, ranging from 4 qubits to 63 qubits. Now, these are motivated by being essential building blocks that we don't really expect to stand alone as impactful quantum applications in the future, rather that they will certainly be core subroutines in larger algorithms. And basically, if you can't compile an adder efficiently, you're not going to be able to compile something like Shor's algorithm efficiently. So this is kind of a good starting point. They run quickly. Yeah. So the second category of circuits that we include are quantum simulation, specifically Crowderized Hamiltonian evolution circuits. Um, and this is motivated by the fact that more and more it's looking like this is going to be like the first killer application of fault-tolerant quantum computing. Um, So we include trotterized simulation of well-known lattice models in both one dimension, two dimension, and 2D triangular lattices. Specifically, we have the Fermi-Hubbard model ranging from 18 qubits all the way up to 128 qubits. The Heisenberg model ranging from 9 qubits to 100 qubits, and the transverse field Ising model from 9 qubits to 100 qubits. And at these circuit sizes, they are certainly very deep circuits, but they're technically still on the edge of what's classically simulable. And that's on purpose, basically, so that we can actually verify the results of our computations on these circuits and the results of our compilers. But it's certainly pushing the edge of what's classically simulable. And then the third category that we include are algorithmic primitives. Basically, these are much more advanced quantum algorithms for a wide range of tasks that in some way or another revolve around linear algebraic computations. And they kind of build upon themselves in complexity. So, for example, quantum phase estimation is composed of controlled Hamiltonian simulations followed by a quantum Fourier transform. And for those who aren't familiar, usually quantum phase estimation aims to find the eigenphase of some unitary operator given an approximate ground state. So this is frequently touted as having applications in quantum chemistry on fault-tolerant quantum computers for finding ground states. But they're, for example, used as a subroutine within the next algorithm that I'm talking about here, HHL. So HHL builds up one level in complexity by including quantum phase estimation and its uncomputation, actually, as well as basically the core subroutine. And we have this ranging from 4 qubits to 21 qubits, solving randomly generated linear systems of equations. And then lastly, we have the quantum singular value transformation. And this is an application that, as an algorithms guy, I'm quite interested in. And QSVT is often described as a grand unification of quantum algorithms, by the way that it effectively parameterizes almost all of the quantum algorithms that we know about today, and certainly many that we haven't discovered yet. And it's kind of amazing that that's true, but it means that if you can efficiently compile a QSVT family of circuits, you can basically efficiently compile almost everything. So we include QSVT circuits of various sizes, implementing the polynomial transformation 1 over x. So this basically makes QSVT a quantum linear system solver with asymptotic complexity better than HHL, but with constant factors certainly larger as well. These are, I think, the largest circuits that we have in the repository. And we have QSVT from 6 qubits to 13 qubits. Right. So now I'm going to talk a little bit about our pipeline. Basically, what is our compilation framework? We assume that we start from Clifford plus RZ continuous rotation gate representation of our circuit. And if the CASM file that's provided is not in that form, then we just quickly compile to that with Qiskit. So with that as the starting point, usually the strategy is to isolate the RZ gates and then use some sort of decomposition algorithm to synthesize Clifford+T representations or approximations of those continuous RZ gates. Stop me if any of this sounds super unfamiliar, but there's basically two leading methods for doing this decomposition of RZ gates. The first one was the Solovay-Kitaev algorithm, and this is really a foundational algorithm because it kind of accompanied the Solovay-Kitaev theorem and showed us that we can efficiently decompose into finite universal gate sets. And the Solovay-Kitaev algorithm is this iterative algorithm that's very general purpose. It's certainly not restricted to decomposing into Clifford+T, but it can be used for that. So it's, in terms of big O notation, it is efficient, but in 2026, it might not be seen as kind of the most cutting edge algorithm that we have. Instead, many people nowadays use an algorithm called gridsynth. So this is not a recursive algorithm, and it's also very specialized for decomposing specifically from RZ gates to Clifford+T. And as a result of that specialization, it's much closer to optimal than Solovay-Kitaev for this specific purpose. So, and when I say near optimal, I mean this kind of in two senses. One, it runs faster, and two, it finds shorter T depth sequences representing our RZ gates. So both introduce some approximation error, but the Solovay-Kitaev algorithm is parameterized by basically the levels of recursion that you're going to use, and the gridsynth algorithm is parameterized by some epsilon precision that you want your gate sequence to be within. So we include both in FTCircuitBench, Solovay-Kitaev more as kind of a comparison against older methods. Gridsynth is much more practical for very large circuits. And from Clifford plus RZ to gridsynth, we have C++ support, which makes it even faster. We have our own C++ implementation of the gridsynth algorithm. The next step, if you want to compile to PBC, this is basically a natural continuation of compiling to Clifford+T. And the rules for this algorithm really come from the well-known paper Game of Surface Codes. So in Game of Surface Codes, they describe how, given a Clifford+T circuit, you can represent your gates as general Pauli rotation gates and measurement gates. And then you can follow a well-defined set of conjugation rules to move all of your Clifford gates to the end of the circuit, basically next to your measurements. And that's what you're seeing up in this corner from here to here. Basically, as you move each Clifford gate past a T gate, it acts upon that T gate by conjugation. And this grows the size of the T gates to kind of general pi over 8 gates rather than single qubit pi over 8 gates. So we kind of call them these T rotation gates. Now, once you have your circuit in this form, you can absorb your Clifford gates. Basically, you don't need to actually do any of your Clifford gates physically. You can classically compute the action of those Clifford gates on your measurement basis and simulate that all classically. And this basically comes from the stabilizer formalism. And we use a specialized Tableau simulator for tracking this evolution of our measurement basis, as well as for all of our conjugations. And even though we have this in Python and C++, this is the type of thing that is much faster in C++ on very large circuits. So yeah, basically at the end of this, we have a sequence of these generalized Pauli rotation gates, as well as multi-qubit Pauli basis measurements, which are these green and these blue blocks. And you can think of the trade-offs of this against Clifford+T as now you don't have any Clifford gates that you need to do. So that's very appealing. On the other hand, now you have all of these potentially very high weight rotation operators and measurement operators. And by weight, I simply mean the number of non-identity terms in your Pauli tensor product, in your Pauli string. So just feel free to interrupt if that doesn't make sense. But you can potentially have weight as high as the number of qubits in your original circuit.
Is that compilation to the PBC? Oh, maybe you're about to say this. I'd say, like, do you know how optimal that is, or how much, like, improvement you could have in that output?
Yeah. So, I mean, to describe optimal, you really need to describe what you're kind of minimizing or maximizing. And usually, the most expensive resources in a PBC circuit are thought to be one, the number of these generalized Pauli rotation gates. So if you don't do any optimization, they certainly grow in size, but the number of them remains the same as the number of T gates that you started with. Um, and then the other expensive resource is just the weights of these Pauli operators. Depending on the error correction code that you actually want to implement PBC circuits on, you might not even be able to implement high weight operators, and you need to first decompose them. So those are the two things that generally you want to avoid. And so far, what I've described doesn't optimize either of those. It just gets you to this PBC form. And then you can start applying kind of optimization passes if you want. And one thing that we include as an optional optimizer is a heuristic algorithm that basically looks at your Pauli rotation strings, and then tries to find nearby ones that commute or anti-commute. So basically, if you have two identical strings with the same phase on them, they can merge into essentially an S gate, right? Like T squared equals S, and then that can be commuted as a Clifford gate into your measurement basis again. Or if you have two identical strings that have opposite phases, those kind of annihilate and cancel out as identity. So we try to find opportunities to do that, but it's not at all feasible to globally optimize this process. So yeah, we invite you to take a crack at beating our heuristic. Right. So then I mentioned we perform numerical analysis at all stages of our compilation pipeline. And these can kind of be broken up into metrics on our Clifford+T stage circuits and metrics on our PBC stage circuits. So here I just include a brief table on only a few of our circuits, but showing the types of statistics that we're interested in. So of course there's the very general purpose ones, total gates, depth, Clifford gates, TNT dagger gates. But then we utilize something called a interaction graph representation of our circuits, and we collect statistics on those as well. So you can see these interaction graphs up here for several circuits, and they are essentially formed by creating a node on your graph for each qubit in your circuit, and then for every 2-qubit interaction between two nodes, you increase the edge weight between that node by 1. So this kind of measurement measures the entanglement structure of your circuit, you can think of. So statistics on this interaction graph can be quite revealing for things like how you're going to partition this circuit into maybe a distributed quantum computing scheme. So the modularity specifically tells you how well your interaction graph can basically be described as multiple individual graphs. And then the number of communities is very closely tied to that. After you've computed modularity, you're given set communities in your graph. We also have the average and standard deviation degree of each node. And that just tells you kind of how closely everything is interacting with everything else. We have graph density, which is kind of a normalized metric for just how much entanglement there is in your circuit normalized by just the size of the circuit overall, the number of qubits. And then here below, you can see for all of our circuits compiled with the GridSynth pipeline, the metrics that we've computed on them. We can collect similar metrics for our PBC circuits as well. We certainly can still create interaction graphs on these PBC circuits, so you'll see some of those statistics. And the only difference in forming interaction graphs for these PBC circuits is that instead of like a single CNOT gate adding an edge weight, increasing an edge weight by one somewhere, basically you look at for each Pauli string in your PBC circuit, you look at all of the qubits that participate in the support of that Pauli string, and you increase all of those pairwise edges by one. But it still essentially measures the entanglement structure of your PBC circuit. But then you'll also see many statistics about the Pauli weights. So I've mentioned this is something that's desirable to minimize. Generally, we want lower weight Pauli operations, and this is because on many platforms, high weight Pauli strings are not native operations, so you need to decompose them anyway. And then we also have some statistics on basically raw versus optimized stats to get a sense of how well our heuristic T-rotation reduction algorithm worked. And you see there's a very wide range all the way from 42.8% reduction on our adder down to no reduction whatsoever on our Heisenberg model. There are several other illuminating ways to look at the PBC operator weight statistics. So we include a couple quick scripts for graphing those given a PBC circuit. So for example, here we have each qubit index along the x-axis, and then the number of PBC operations that it basically participates in throughout your circuit. And this is probably most helpful for mapping these logical qubits down to the physical qubits on your hardware. Essentially, if you see something like for our 64 qubit adder, we have basically these very like this high variance with some qubit indices participating in many PBC operations, some participating in very few. And we'll most likely want those qubit indices that participate in many PBC operations to be more centrally located or more connected when we actually map it to our hardware, versus something with essentially no variance, like the 2D Heisenberg model. We can't expect to get much benefit from a smart mapping strategy to hardware. This is another representation of our PBC operator weights. So over here on the x-axis, we have the actual weight of the operator, and then the y-axis is number of counts. So it's a histogram over weights. And we can see that these are all Hamiltonian simulation circuits, right? But they look quite different from one another. And it's very interesting to see that, for example, the 100 qubit 1D easing model is almost all very low operator weights. So this should be pretty easy to implement on any hardware, versus something like the Fermi-Hubbard model has very many high weight Pauli rotations. And maybe depending on the error correction code, you'll be able to implement this, but it won't be as straightforward if you don't have native high weight Pauli operators that you can access. We also include a script for essentially fingerprinting your PBC optimization algorithm should you choose to use your own. So this is what it looks like on our heuristic that I briefly described before. And I mentioned that there's kind of two things that may be desirable to minimize. One is just the number of rotation operations. You want to cancel as many out as you can. And two is the Pauli weights of these operations. It would be better to have only low weight operations generally. And we can see this is basically our comparison of our raw PBC circuit versus post-optimization. For many of these circuits, if we've reduced more of our Pauli rotation operations, we've also increased the average weight. So this blue going below 0 means that the average weight has actually increased. And the takeaway from that is basically that our heuristic is good for minimizing or good for canceling out low weight operators, but it's not as good at finding these high weight operators that are particularly expensive and canceling those out. So it might be a good future direction to design an optimization path that specifically looks for those. And lastly, we have just these different kind of circuit representations where you can quickly look at where the expensive resources lie in the space-time kind of layout of your circuit. So over here we have on the left representations of our Clifford+T circuits where the color bar just represents the number of T or T dagger gates in some number of binned operations. So if we say from time step 0 to time step 10, there's like, I don't know, 100 T gates, for example, on qubits 16 through 20. We can see that that's really where we need to focus our resources as we're running this algorithm. And it also kind of just gives you this structural decomposition of your algorithm. You can see that, for example, the top is the HHL circuit, and I've described it as being essentially composed of quantum phase estimation and then uncomputation of that quantum phase estimation, which gives it this very symmetric structure. But you also really see that the qubit registers up at the top, I think this is 17 through 20, are where you initialize your B vector. And then by the end of the algorithm, that should be your X vector that represents the solution to your linear system of equations. And you see very quickly with this kind of top-down view that that is the expensive part of the algorithm. You want those qubits to be very central with high connectivity and close to your magic state factories, for example, throughout this algorithm, if possible. Over on the PBC representation to the right, we use the color bar to represent any non-identity operator. So it's kind of an analog of what we're doing with the T gates, but now it's the supports of our generalized T rotation operations. And what's really interesting is I think most of us have learned about quantum computation through the gate-based model, and maybe we find that more intuitive. It is really not intuitive at all what the Pauli weight distribution over space and time will look like for a PBC circuit. Even if we know exactly what the Clifford+T or gate-based representation of that circuit is. For example, nobody that I know would have been able to predict that for this 1D Fermi-Hubbard model, we essentially have a completely random chaotic looking distribution of Pauli operator weights. Whereas for the 1D Ising model, it still retains this strange looking structure, and we haven't even gotten close to figuring out why exactly that occurs. But I think these PBC circuits are much less intuitive, which means that there's a lot more opportunity for using metrics and visualization tools to kind of try to pick them apart. So in terms of use cases of FTCircuitBench, I think different communities might be able to use it quite differently. So in any case, benchmarking across the computational stack is very important for exposing where you can co-design parameters rather than optimizing them individually. And I would expect for the architecture and compilation community, hopefully you use it to quantify the improvements of your architectural designs and compilation algorithms over these baseline circuits that we provide in FTCircuitBench. However, I also urge any quantum algorithms and applications people to take a look at the package and just upload your CASM files and take a look at what it looks like. That's very easy to do, but I think it can be quite illuminating to see the different costs of your circuit in different computational models. And it's really important for algorithm developers, I think, to consider lower level implementation details and resource costs rather than just looking at kind of big O scaling of their algorithm. So for example, maybe you find that you can greatly reduce resource costs by having some approximate version of your algorithm, or maybe some probabilistic repeat until success type implementation of your algorithm. And if you have a high probability of success, but you greatly reduce resource costs, that might be a very worth it trade-off. And I think, just one more quick story to tell about kind of our process of putting FTCircuitBench together. So I've repeatedly touted the importance of trying to co-design parameters and find global optimizations rather than these local optimizations at each stage of the compilation pipeline. And one really interesting example of this we found quite accidentally when we were putting the package together. And it's obvious in hindsight, maybe, but I think it's an example of where different types of quantum computing researchers don't necessarily think about other stages of the compilation stack. So we were putting together compiled versions of our Hamiltonian evolution circuits, where we had used 20 Trotter steps to approximate continuous unitary evolution. Now, if you know anything about Trotterization, basically the more steps that you do, the smaller the angles of your RZ gates will become when you represent it in a Clifford+RZ circuit form. And that makes sense because there's just more of those RZ gates, but smaller angles, smaller evolution times for each one. And eventually, if you're experimenting with decomposition precision, for example, using GridSynth to get from Clifford+RZ to Clifford+T, you'll find that if those angles cross some threshold, if they get small enough, then essentially the closest Clifford+T sequence to your RZ gate is just an identity gate, right? Now that's kind of obvious when you think about it, but not too many people are thinking both about Trotterization and about GridSynth decomposition at the same time. So we were finding that with our 20 Trotter step Hamiltonian evolution circuits, once we've gotten all the way to our PVC representation and then ran our heuristic optimizer on it, all of the T rotation gates simply disappeared. They completely vanished, which we thought was a bug in our code for the longest time. But really tracking it back, it turns out it's just because it's an unphysical representation of the circuit. All of our RZ gates basically collapse to identity gates because the combination of our Trotter steps parameter and our GridSynth decomposition parameter did not play well. And for that reason, we included the same batch of Hamiltonian evolution circuits, but with only 5 Trotter steps instead of 20. And we found that we didn't have this issue. So I think that's just one example out of very many of how thinking about different parameters all the way on different stages of your stack is important. And with that, I'll take any questions. Thank you.
Hi. I guess first I wanted to say thank you. This is really useful, especially the the bank of circuits that you could benchmark on. And I guess my question was about what kind of compilers did you consider, or what kind of compilation methods? And if I want to check, for example, different ways, for example, I could write a plugin for Qiskit. can I then use that compiler? Or, yeah, just I guess which compilers are you considering?
Yeah, you can use, I mean, we encourage you to use anything you want, and especially to try to, well, it shouldn't be hard to beat our baselines, but to evaluate the effectiveness of your compilers against our baselines. So to get from some arbitrary chasm file to a Clifford plus RZ representation, we just use Qiskit with like optimization level equals 0. To get from Clifford plus RZ to Clifford+T, we have basically these two pipelines. We can either use GridSynth for that, or we can use Solovay-Kitaev. Um, if you want, my personal opinion, if you want like a competitive, fast, near optimal T-depth way of doing this, you should go the GridSynth route. And particularly for the GridSynth route, we have both uh, I think the PyGridSynth implementation as well as our own C++ implementation for especially large circuits where it gets slow. Now from Clifford+T to PBC, we wrote our own compiler for this. So we use, I didn't really talk about it much, but um, we know the rules from Game of Surface Codes, but that doesn't really give you a direct software implementation for doing this compilation step. It just tells you kind of the general rules to follow, right? Um, and what we do for this stage, so basically along step 2, is we use this Tableau representation. I see a hand raised.
Yeah, for the PBS one, I just wanted to mention that IBM has open sourced a tentative compiler doing that. So you might want to try it out.
Yeah, I think everyone's been doing similar stuff at the same time. I believe Penny Lane, I haven't used it myself, but also over the summer came out with a PVC compiler. Um, So I think there's been a lot more focus on PVC representations recently. I'd be very curious how fast theirs is compared to ours. We have a Python implementation of this Tableau simulator, which is correct, but not really state of the art in terms of speed. And then we have the same algorithm in C++, which is blazing fast. Um, so there's still wait time for some of our circuits with 10 to the 7, 10 to the 8 gates, but it's I think reasonable. Um, so this part we've implemented ourselves. Does that answer your question?
Cool, thank you. Yeah.
And I should mention that the C++ acceleration that I'm speaking of is a optional dependency of FTCircuitBench, so you can opt to not download it. It's part of a package called NWQEC that RPNNL group released at the same time, and there's a specific paper for really the low-level implementation optimizations that they did for that. So you don't need to download this NWQEC package to run FTCircuitBench. We have everything in Python as well, but I would strongly recommend it if you actually want to compile these massive circuits.
You mentioned at the beginning, part of a motivation is targeting kind of the surface code or the bicycle codes. Are you mad? Is that would be like a fourth layer here where you get down to these either PBC or whatever the code wants as its input, and then you tack on that compiler and you use these similar kind of analysis tools to see what that spits out?
Yeah. So this kind of gets us to that point, and then from there you can go and evaluate stim type uh, compilation, and we don't deal with like logical error rates or anything like that. We just get to that kind of abstract model of computation that supports fault-tolerant proposals.
So Evan had a question over in the chat, whether the implementations of the different compilers that you shared are fully in NWQEC, or there's some that are only in FTCircuitBench.
So if you opt to not download NWQEC, everything in FTCircuitBench will work. We have everything in Python. If you do also download NWQEC, then the slow parts of it will just work much faster. It's the same algorithm.
And what about the other direction? If you just download NWQEC, will you have every...
So if you just download NWQEC, you will have Clifford+RZ to Clifford+T with their C++ grid synth. And then you'll have Clifford+T to PBC with optional optimization. You won't have nearly as much, like, basically numerical analysis and visualization tools and things like that. So if you really just want to build this into your own compiler and not use it as much for I don't know, resource estimation and things like that, yeah, just NWQEC is very efficient.
Any other questions? Okay. If not, well, yeah, thank you, Adrian, again for the presentation and discussion. And yeah, thanks everyone for joining.
Thank you so much.
Thank
Thank
you.
you.